Today we are going to discuss about the state space model of armature control DC motor and field control DC motor. The first topic is state space model of armature control DC motor. Let us start. So we all know the speed control of a DC motor can be done in two ways. The speed can be varied directly with respect to the armature voltage and inversely with proportional to the flux. Here we are doing our armature control DC motor, that is this one. The simple process of obtaining the state space model is to obtain the differential equation governing the system, and from there defining the states and interrelating the states with the differential equations. The final form of the state space form of the system is x dot is equal to ax plus bu and y is equal to cx plus du. When the system differential equations governing the system, when the differential equation is obtained, once the differential equation governing the system is obtained, the other part we have done in the previous lecture. From the differential equation, how to get the state space model, it is the same. So the first task is to obtain the differential equation of this particular system. This speed control system is an electromechanical system. It consists of electrical circuit and mechanical circuit. The electrical circuit is the armature circuit, and the mechanical system is the motor shaft connected to the load, external load. The motor shaft connected to the external load. This is the equivalent circuit. In the equivalent circuit, some textbooks might represent your field circuit and some might not represent. So don't worry about that. Different textbooks have their own way of representation. Because here our field is taken as constant, we may represent or may not represent the field circuit. It doesn't make any difference. So coming to the armature circuit, here the armature circuit is consisting of armature supply voltage or terminal voltage, by which the armature current flows and is connected to the motor shaft. Here the armature circuit winding will be consisting of armature resistance and armature inductance. The back EMF will be generated here, and this motor shaft is connected to the external load, and the external load is having a moment of inertia of B and viscous coefficient of B. Now let us see how to first obtain the differential equations. So before starting getting the differential equations can be obtained from the equivalent circuit. So let us see what are the terminologies and what are the different parameters involved. What are different parameters involved in this? The different parameters are RA is equal to armature resistance, ohms in ohms, LA is equal to armature inductance, IA is equal to armature current, V is equal to terminal voltage, EB is equal to back EMF, KT is the torque constant. I'll say about this again. Just remember KT is equal to torque constant. These are all the parameters corresponding to the electrical circuit. And coming to the mechanical circuit, the torque divided by the motor, Newton meters, angular displacement of the shaft, or you can also call it the output, angular velocity, radians per second, or you can also write omega in terms of d theta by dt. And coming to the load part, moment of inertia, kg meter square per radians, and physical coefficient or viscous coefficient, Newton meter per radian second, and kb back EMF. These two constants I'll come back to you later. So the first step is to obtain the differential equation. As I already said, is an electromechanical system, which is a combination of electrical and mechanical. So I will take the mechanical equivalent circuit and electrical equivalent circuit separately, and from this we are going to derive our differential equations. So this is the equivalent circuit of electrical system, or the supply voltage, nothing but armature terminal voltage, VA, armature resistance, armature inductance, and back EMF. The drop at rest, the current passing through this is armature current IA, and the drop in the armature resistance is IA into RA, and drop in the inductor is L di by dt, LA dia by dt. So simply applying your Kirchhoff voltage law, we have the applied voltage or source voltage is equal to sum of voltage drops IA RA is LA dia by dt plus EB. So we will take this as equation number 1. Also we know the torque of a motor is directly proportional to armature current. Therefore torque is proportional to armature current. And in order to take out this proportionality constant, I have to introduce some constant, and this constant is called as torque constant, which we have written here. Torque constant is equal to Kt. T is equal to torque constant into Ia. Let us take as equation number 2. Now coming to the mechanical part is the mechanical motor shaft. This is the motor shaft, which is having a displacement, angular distance of theta, and the motor torque developed is T, is connected to the external load, and the load is having the moment of inertia J and viscous coefficient B. Now this is the mechanical circuit, and corresponding to the mechanical circuit, the force balance, the torque balance equation is written as motor torque plus torque is equal to torque due to moment of inertia and torque opposite by viscous coefficient. From our available knowledge, torque is equal to J d square theta by dt square plus B theta by dt. We will take this equation as equation number 3. The other equation is the back EMF is proportional to the angular displacement, or you can also call it as speed. That is, you can recollect your equation. Back EMF is written as phi NZ P by 60 into A. From this equation, meaning all terms are constant, because we are using the armature current, flux is constant. Therefore, back EMF is proportional to En, or you can also write omega or d phi by dt. Taking out this proportionality constant, we have EB is equal to KB. This is nothing but the back EMF constant, what we have already defined here, back EMF constant, into d theta by dt. These are the four. This is the fourth equation. So these are based on these 4 equations, we are going to get the 2 differential equations. So you see the equation number 1. The equation 1 is consisting of VA drop across RA, LA and EB, and also your equation number 4 is EB. Therefore, if you substitute your equation number 4 in equation number 1, it becomes an one differential equation. Similarly, you can see your equation number 2 is a torque, and equation number 3 is also torque of motor torque developed. Therefore, you can combine equation number 2 and equation number 3. This will be another differential equation. Therefore, the total system is now is given by the 2 differential equation. One is corresponding to the electrical part and another one is corresponding to the mechanical part. So substituting equation number 4, that is EB in equation 1, what we have is we have VA is equal to drop across resistance plus drop across inductance and back EMF. So back EMF substitute, that is from equation number 4, EB is equal to KB d theta by dt. Substituting this. Now let this be equation number 6. And similarly from equation number 2 and 3, substituting your torque equation, torque is equal to Kt into Ia is equal to J d square theta by dt square plus B theta by dt. Now here we have got our 2 differential equations, and from these 2 differential equations, now we are supposed to identify the new states and relate these states in terms of this differential equation and obtain your first order differential equation in terms of your states. X dot is equal to Ax plus Bu. That's the form. So what are your states and how many states do we have here? So here we are having, the system is having 2 parts, electrical and mechanical. So for any electrical circuit, the total number of states are given by the total number of energy storing elements. Here in our electrical circuit, the total number of energy storing elements is equal to only 1. Here Ra is energy dissipating element and La is the only available energy storing element. Therefore, corresponding to electrical part, we have 1 state. And coming to the mechanical part, we have angular displacement and angular velocity, theta and omega as the states. Therefore, the total number of states for this system will be equal to 3. I'll repeat once again, for electrical system, the total number of states is given by the total number of energy storing elements. For example, if we have 2 inductors, with the total number of states will be equal to 2. We have 1 inductor and 1 capacitor, the total number of states are equal to 2 again. So for any electrical circuit, the total number of states is equal to the total number of energy storing elements. So here we have one state, and the state for inductor, the state is given by the current to the inductor, and in this case the current to the inductor is IA. Therefore one state corresponding to electrical circuit is x1 is equal to IA, and the other two states x2 is equal to angular velocity and angular displacement. Some textbooks might give x2 is equal to theta and x3 is equal to omega. It doesn't make any difference. You can choose, it's all about how you choose. Your final dynamics matrix A will come as per your states what you have taken. So you might some textbooks might give as x1 is equal to omega, x2 is equal to theta, and x3 is equal to IA. So don't worry about that. So they might take electrical states as second and then mechanical states as first. So don't get confused about x1, x2, x3. What should be the x1? Just concentrate on the states. What should be the states? So whether you take electrical as first state or the last state, it doesn't make any difference, obviously. So the next is to relate the states in terms of first order differential equations. So x1 is equal to IA. Therefore x1 dot is equal to dx by dt. x2 is equal to omega or d theta by dt, or x2 dot is equal to d square theta by dt square, and x2 is equal to theta and x3 is equal to d theta by dt. That. So now integrate it in this. We have x2 dot is equal to theta, and already we have taken x2 is equal to d theta by dt. Therefore xt dot can be written as x2. This is one of the state equation we directly found here, we have directly got here. But x1 dot is equal to dx1 by dt and x2 is equal to d square theta by dt. That means we are supposed to derive x1 dot and x2 dot from the available two equations. Now let us take the first equation, an electrical equation, or from here you can call it as equation number 5. And in equation number 5 you have VA is equal to V is nothing but the input, and here in state space we represent input with U. Therefore I am taking VA is equal to U. U is equal to RA into IA, and from here you can see IA is equal to x1 plus LA DIA by dt, and again IA is equal to x1, therefore dx1 by dt plus KB into d theta by dt. Again d theta by dt is equal to x2. So here you can see dx1 by dt is written as x1 dot. Therefore U is equal to RA x1 plus LA x1 dot plus KB into x2. Keeping this LA x1 here and taking this RA and KB term that side, you have LA x1 dot is equal to U minus RA x1 minus KB x2. Dividing this equation with respect to LA, we have, or cross multiplying this, we have x1 dot is equal to U by LA minus RA by LA into x1 minus KB by LA into x2. This is the saddest state equation, first order differentiation, in terms of first order differentiation. So x1 dot. So this is the other equation. So we have got here x3 dot in terms of x2, one differential equation in terms of state, and another differential equation in terms of states. So the remaining is x2. Let us, in order to get this x2, which is in terms of d square theta by dt square, let us take the mechanical differential equation, that is the equation number 6. So from equation number 6 we have kt into IA is equal to j d square theta by dt square plus b d theta by dt. From this you can write as kt into, again IA can be written as x1, some of the states what we have written here already, and j d square theta by dt square, again you can go back to this here, it is d square theta by dt square can be directly written as x2 dot plus b dx by dt, b d theta by dt is written as x2. Therefore, k1 kt x1 is equal to j x2 dot plus b x2. So taking this b into x2 on the other side, we have j x2 dot is equal to kt x1 minus b x2 dividing by j x2 dot is equal to kt by j x1 minus b. Again we have got here x2 dot or derivative of state in terms of states. So we have three equations: x1 dot in terms of x1 x2 input, x2 dot in terms of x1 x2 and x2 dot. Therefore, so combining these three equations and representing in terms of your matrix form, x1 dot x2 dot x2 dot is equal to, that's x dot is equal to, this we can write it as x dot is equal to coefficient of first equation corresponding to x1. This is the input and this is the dynamics. Therefore, I am dividing the equation into two parts. One is in terms of dynamics and in terms of your inputs. So the dynamics is given by coefficient of x1 is Ra by La, coefficient of x2 is Kb by La, and x3 is 0. And your input is, I am separating inputs here. We have 1 by La into this. Similarly, writing the x2 kt by j minus b by j 0 and no input term corresponding to x2 dot. Similarly, x3 dot is equal to 0, only simply x2 and this. So this matrix is your A and this is your B. Now let us not put much brain what about the Y matrix, because Y matrix is corresponding to the measurement where we want to exact measure. So I assume here, because we are not given specifically where to measure the output, so I would like to measure the armature current, angular displacement and angular velocity, all the three. At times if they specify to measure the output any at given stage, or some textbook might give, because it's an mechanical system, electromechanical is not DC motor, the output is nothing but displacement of the shaft. Therefore some textbooks might give the output is equal to only y is equal to theta. In that case y is equal to simply x3. So here in this case I am taking I would like to measure all the three parameters, Ia, omega and theta, and therefore again relating these in terms of states, y1 is equal to x1, y2 is equal to this x2 already which we have defined, and y3 is equal to x3, and giving in terms of a matrix on y1, y2, y3 is equal to 1 0 0 x1, well this y1 is equal to x1 and y2 is equal to x2 and y3 is equal to x3. So this will make my simple max. So if you say if you ask sir why we have a simple output, why output in terms of theta is well and good, you can like that also. If you want to have a discussion why we want to measure all the three, it's a DC motor and just you want to measure the output as theta, which is nothing but the angular displacement. In this case y is equal to theta, and this theta can be written as this theta is given as x3 in this case. So now my y matrix will be 1 0 0 x1 x2 x3. So sorry correction once again, 0 1 0 0 1 0 into x1 plus 0 into x2 plus 1 into x3. This will be my output matrix. You can do in whatever manner you like. Also, if you are interested wherever you want the output to be measured, you can take this. It's not a big deal at all. So you can either use this one as y matrix, or if you want to measure all the three variables, you can use this one. In this case the identity matrix, this will be your matrix C. If you want to, if you are interested only in measuring the angular displacement theta, then this will be a matrix theta. So it doesn't make any sense. It's all about where you want to measure and where you are intended to measure the output. Right. Thank you.